All right, so here's part two, and this is something that's kind of cool because previously we learned, like, if you find critical numbers, which is when the derivative is 0 or undefined, usually it's 0 that's more important, but sometimes every now and then you'll get an undefined that's important. But if you ever get a critical number, which is when your derivative equals 0, you know that it's either a max, a min, or an inflection point. But you don't know which one it is. All you know is, hey, my derivative equaled 0 when x was 5, for instance. But you can actually figure out which one of these three it is. Because if you find that point, let's say it was 5, because I just made that number up. If you take that answer and you put it into the second derivative, if you plug the 5 into the second derivative and it came out greater than 0, well, you have not just a random point that could be a max, a min, or an inflection point, you actually know it's a minimum. I know it's counterintuitive because you see greater and you want to say maximum, but remember, greater on the second derivative means concave up. If I draw a quick picture, up like a cup means that bottom point is a minimum. Okay, if you plug your answer into the second derivative and it comes out negative, less than 0, I know you'd want to say min, but less than 0 on second derivative means down like a frown. Well, if you look at that picture, that doesn't have a minimum, that has the highest peak on the hill. So that would make a max. And if you plug a number into your second derivative and it equals 0, well, we just kind of talked about that on the previous page of notes, that is an inflection point. So it's kind of cool. You don't even have to look at the graph. You don't even have to make a table to figure out if you have a max or min or an inflection point. You just can use this second derivative test. Okay, so let's do one example of that. All right, so here's an equation or question. Use the second derivative test to find any extrema or inflection points. So we actually want to find them, and we want to know, and we want to say whether they're max or mins on our extrema. So here's our crazy equation. This is a huge, way off the graph. You wouldn't want to graph this thing to do it, or to find them with your graphing calculator. So if I have x to the fourth plus 8x to the third plus 200, and I want to find extrema, I want to find all my max and mins without having to graph it, well, I know that, well, where do extrema occur? Question. Well, they occur at critical numbers. That's where the derivative is 0 or undefined. So the first derivative. So I can find out when my max or mins would happen by using my first derivative. So that would be a good thing to find first. So I'm going to find my first derivative, which is just 4x to the third plus 24x squared. Right? The 200 goes away because you take the derivative. And this is never going to be undefined because I don't see a radical and I don't see a fraction. So I can just simply set it equal to 0 and solve it. And this one's pretty easy to solve because you can take out a GCF. They're both divisible by 4 and x squared. So I'll take out a 4x squared. What's left from this one is x. What's left from that one is 6. And then if this times this equals 0, either this part equaled 0 or that part equaled 0. So I got 0 and negative 6. So I got two places where it's either a max, a min, or an inflection point. I know that. These are the only two places on the whole graph. I don't even need a graph. And how I'm going to check it is with the second derivative test. I will test these points out, and I can tell without a graph or a table, I can tell whether that's a max, a min, or a 0 at that point and that point. So I need my second derivative first before I can do that. So if my first derivative was this, my second derivative is the derivative of that equation. So it's going to be 12x squared plus 48x, right? And then I need to plug in my two numbers here. I need to say, okay, so f double prime of 0 is going to be 12 times 0 squared plus 48 times 0, which is 0. What's that tell me? Well, that tells me that I have myself, if the second derivative equals 0, it's not concave up, it's not concave down, I have an inflection point at 0 comma something. We'll figure that out in a minute. I can also do this for my other point. And without a graph, I can actually determine negative 6 squared plus 48 times negative 6. I can determine if this is going to be max or min or an inflection point. So if I plug this one in, I don't know what it comes out to be, but I know it's going to be positive. Hold on, we can check it out. So, oh yeah, because this is positive. So 12 times 36 plus 48 times negative 6, 144. It doesn't matter as much that the 144, it matters that it's positive. And if it's positive, you have an equation that's, or sorry, a curve that's concave up like a cup. So what I just found was a minimum. Oh, there's an inflection point here. I found that it's a minimum at negative 6 comma something. And my only thing left to do in this problem is to figure out what those somethings are. And you can do that easily by plugging in the two x values to your original equation. So if I plug a 0 in there, I get a 200. That one's actually pretty easy because let's go away. And then if you plug a negative 6 in, it goes way down to negative 232. You have a minimum there. I don't even need my graphing calculator to figure that out. It would take a while if I did, because you'd be way off the screen and to find them. So anyway, it's pretty cool. All right, one last example. Just kidding, no last examples. That's it. So that wasn't bad. Little 7-minute video. All right, I hope you enjoy that stuff, and we'll see you when we see you. All right, talk to you later, people.